It's a quiet spring morning in northern Ukraine. The year is 1986, and the Soviet Union stands as one of the world's two superpowers. In the city of Pripyat, families are waking up to what they believe will be just another ordinary Saturday. Children prepare for weekend activities while their parents plan leisurely days ahead. Just a few kilometers away, the Chernobyl nuclear power plant hums with its usual mechanical rhythm. 4 massive reactors work around the clock, generating electricity for millions of Soviet citizens. The facility represents the pinnacle of Soviet engineering prowess, a testament to their technological advancement in the nuclear age. But beneath this facade of normalcy, a series of decisions and circumstances are converging that change the course will forever of history. What happens in the next few hours will not only devastate an entire region, but send shockwaves across the globe, fundamentally altering how humanity views nuclear power. This is the story of the Chernobyl disaster. The RBMK reactor, a Soviet design unlike anything used in the Western world, powers the Chernobyl facility. Standing nearly as tall as a 10-story building, these graphite-moderated reactors were considered revolutionary when first constructed. The design allowed for continuous refueling during operation, making them incredibly efficient for power generation. Reactor number 4, commissioned in 1983, was among the newest additions to the complex. Its massive concrete structure housed over 1,600 fuel channels, each containing uranium fuel assemblies that sustained the nuclear chain reaction. Control rods made of boron carbide could be inserted or withdrawn to regulate the reactor's power output. On the evening of April 25th, the night shift arrives for what they expect to be a routine safety test. The test itself was not unusual. It was to determine design whether the reactor's steam turbines could generate enough electrical power to run essential safety systems during a brief power outage. This experiment had been attempted before at other nuclear facilities, but never successfully completed at Chernobyl. The reactor operators begin reducing power levels in preparation for the test. According to the procedure, they need to bring the reactor down to a specific power level where the experiment can be safely conducted. However, what should have been a straightforward process quickly becomes complicated. At 2 o'clock in the morning on April 26th, the reactor's power output drops far below the intended level. Instead of operating at the planned 700 megawatts, the reactor is producing only 30 megawatts. This dramatic reduction creates an unexpected problem. The reactor has entered what nuclear engineers call a poison well, a condition where xenon gas, a byproduct of nuclear fission, builds up and absorbs neutrons that would otherwise sustain the chain reaction. The operators face a critical decision. They could abort the test and restart the reactor properly the following day. Or they could attempt to override the safety systems and proceed with the experiment despite the dangerous conditions. Under pressure to avoid disappointment, complete the test, and intimidate their supervisors, they choose the latter option. Deputy Chief Engineer Anatoly Dyatlov arrives to oversee the final stages of the experiment. A veteran of the Soviet nuclear program with decades of experience, Dyatlov is known for his demanding nature and unwillingness to accept delays or excuses. His presence adds additional pressure to an already tense situation. To compensate for the low power output, operators begin withdrawing control rods far beyond normal limits. They pull out nearly all the control rods, leaving the reactor in an extremely unstable state. The few remaining rods provide minimal control over the nuclear reaction, creating conditions that violate multiple safety protocols. The reactor's emergency cooling system is also disconnected as part of the test procedure. This system would normally flood the reactor core with water in case of an emergency, but the test requires it to be offline to simulate realistic conditions during a power outage. As the experiment continues, the reactor becomes increasingly difficult to control. Power levels fluctuate wildly, and the operators struggle to maintain stable conditions. The reactor core begins heating up rapidly as the nuclear chain reaction accelerates beyond safe parameters. Senior reactor operator Alexander Akimov notices alarming readings on his instruments. The reactor's power output is climbing dangerously high, and multiple warning systems are activating. He turns to his colleague Leonid Toptunov, a young engineer who has been working at the plant for less than a year, and expresses his growing concerns about the reactor's behavior. The cooling water inside the reactor begins turning to steam at an accelerated rate. This steam displacement reduces the water's ability to moderate the nuclear reaction, causing power levels to spike even higher. The reactor enters what nuclear physicists call a positive feedback loop, a runaway reaction where increasing power creates conditions that further increase power. At 1:23 in the morning, the situation reaches a critical threshold. Akimov realizes the reactor is completely out of control and makes the decision to initiate an emergency shutdown. He presses the AZ5 button, which should insert all control rods simultaneously and halt the nuclear reaction. But instead of stopping the disaster, this action triggers the very catastrophe they were trying to prevent. The control rods, designed with graphite tips that actually increase nuclear activity before the boron absorbs neutrons, cause a massive power surge as they descend into the reactor core. The reactor's power output skyrockets to more than 10 times its normal operating level in a matter of seconds. The fuel assemblies begin to melt and disintegrate under the extreme heat. Steam pressure builds rapidly throughout the reactor vessel, as temperatures soar beyond anything the structure was designed to withstand. The operators in the control room watch helplessly as their instruments register readings that seem impossible. The reactor that had been limping along at 30 megawatts just hours earlier is now generating more power than it had ever produced in its entire operational history. What happens next will transform this failed safety test into one of history's most devastating nuclear accidents, sending radioactive material across multiple countries and creating an exclusion zone that remains uninhabitable to this day. The first explosion tears through reactor number 4 at exactly 1:23 and 47 seconds. The massive concrete and steel structure, weighing over 1,000 tons, is lifted into the air like a toy before crashing back down. The sound reverberates across the entire complex, shattering windows in nearby buildings and sending tremors through the ground. In the control room, the lights flicker and then go out completely. Emergency lighting kicks in, casting an eerie red glow across the instrument panels. Akimov and his team are thrown from their positions as the building shakes violently. When the trembling stops, they find themselves surrounded by sparks, smoke, and the acrid smell of burning electrical equipment. Toptunov struggles to his feet and looks at his control panel in disbelief. Every gauge that had been measuring the reactor's condition now shows nothing. The instruments designed to monitor the nuclear core have gone completely silent. He turns to Akimov with a look of confusion and growing terror. Outside, chunks of graphite and radioactive debris rain down across the facility grounds. These pieces of the reactor's core, some glowing with an otherworldly blue light, scatter across an area spanning several hundred meters. Plant workers who venture outside to assess the damage have no idea they are through walking some of the most radioactive material on Earth. The explosion has blown apart the reactor's protective systems and exposed the nuclear fuel directly to the atmosphere. Without the concrete and steel barriers that normally contain radioactive materials, deadly particles begin streaming into the night sky. An invisible column of contamination rises high into the atmosphere, carried by wind currents that will eventually spread this poison across vast distances. Dyatlov, who had been coordinating the test from a separate room, rushes to the control area. His first instinct is denial. Years of working within the Soviet system have taught him that admitting to such a catastrophic failure could mean the end of his career, or worse. He surveys the destruction and makes a decision that will cost precious time in the critical hours ahead. Rather than immediately calling for emergency assistance, Dyatlov orders his subordinates to continue trying to pump water into what remains of the reactor. He refuses to believe that the reactor core has been destroyed, insisting instead that the cooling system can still bring the situation under control. This decision proves disastrously wrong, but it reflects the culture of the Soviet nuclear program where admitting mistakes was often more dangerous than the mistakes themselves. Meanwhile, the plant's firefighting brigade receives reports of blazes breaking out across the facility. Led by Lieutenant Vladimir Pravik, these brave men have no understanding of the radioactive nightmare they are about to enter. Armed with conventional firefighting equipment, they begin battling flames that are consuming the turbine hall and other structures damaged by the explosion. The firefighters climb onto the reactor building's roof, directly above the destroyed core. They work frantically to control the spreading fires, unaware that they are absorbing lethal doses of radiation with every breath and every step. The graphite blocks scattered around them emit radiation levels thousands of times higher than what a human can safely tolerate. As the night progresses, plant officials slowly begin to grasp the magnitude of what has occurred. Phone calls start going out to regional authorities, but the initial reports dramatically understate the severity of the situation. Local officials are told there has been a minor accident at the nuclear facility, with no immediate danger to surrounding populations. In Pripyat, residents remain completely unaware of the catastrophe unfolding just kilometers from their homes. The radioactive plume passes silently over the sleeping city, depositing contamination on playgrounds, schools, and apartment buildings. Children who will play outside the next morning have no idea they are being exposed to radiation levels that will affect their health for the rest of their lives. The Soviet Union's secretive nature works against any rapid response to the crisis. Information about the accident is tightly controlled, shared only among the highest levels of government and nuclear officials. This delay in acknowledging the true scope of the disaster prevents timely evacuations and medical treatment for those most at risk. By dawn, the destroyed reactor continues burning, sending more radioactive material into the atmosphere with each passing hour. The graphite fire proves incredibly difficult to extinguish, as conventional firefighting methods are useless against this type of blaze. The burning reactor creates its own weather system, with hot gases rising and creating wind patterns that spread contamination in unpredictable directions. Soviet authorities face an unprecedented challenge. They must find a way to stop the reactor fire, contain the radioactive contamination, and manage the growing health crisis among plant workers and emergency responders. Each decision they make in the coming days will determine whether this disaster remains localized or becomes a global catastrophe that affects millions of people across multiple countries. The Chernobyl disaster stands as one of the most profound lessons in modern history about the devastating consequences of human error, institutional failure, and technological overconfidence. What began as a routine safety test became a catastrophe that forever changed how we understand nuclear power and its risks. The explosion at reactor number 4 released radioactive material equivalent to multiple atomic bombs, contaminating vast areas across Ukraine, Belarus, and Russia. The immediate death toll was relatively small, but the long-term health effects continue to impact thousands of people decades later. Entire communities were permanently displaced, creating a 30-kilometer exclusion zone that remains largely uninhabited today. Perhaps most tragically, this disaster was entirely preventable. The combination of flawed reactor design, inadequate safety protocols, and poor decision-making under pressure created the perfect storm for catastrophe. the operators who pushed forward with the test despite dangerous conditions, the engineers who designed control rods with fatal flaws, and the officials who prioritized secrecy over public safety all played roles in this unfolding tragedy. Yet, from this darkness emerged stories of extraordinary heroism. Firefighters, plant workers, and cleanup crews risked their lives to contain the damage and prevent an even worse disaster. Their sacrifices helped limit the contamination and saved countless lives across Europe. Today, the ruins of reactor number 4 remain entombed beneath a massive steel structure, a monument to both human fallibility and resilience. The lessons learned from Chernobyl have improved nuclear safety worldwide. But the scars left by that April morning serve as a permanent reminder of what can happen when technology, politics, and human nature collide with devastating consequences.